Hey folks, here we get started in chapter 7, and in section 7.1 we're going to look at, we're going to revisit inverse functions. Inverse functions is something that you would have seen in college algebra. That's when you first would have seen it, and the vast majority of this section is going to simply be a review from college algebra, but it's a really important review, so we're hitting the highlights of inverse functions. There will be a little bit of calculus sprinkled in this section as well. So folks, this figure over here to the right, it illustrates the basic relationship between a function and its inverse function. So, for example, here's x. Function f will take x. See, this is function f, and it drops it off at f of x. This set is the domain of the function. This set is the range of the function. So what an inverse function will do is it takes f of x and it sends you right back to where you started. And that's the notation we use for inverse function, and we read that as f inverse. This set will be the domain of the inverse function, and this set will be the range of the inverse function. So in short, an inverse function undoes what the function has done. And also, I just mentioned it, but I'm going to mention it again. The relationship between the domain and range for a function and its inverse function is exhibited in this figure that I have here. That is, the domain of the function must equal exactly the range of the inverse function. Likewise, the range of the function must equal exactly the domain of the inverse function. And let's revisit this old definition that you would have seen way back in college algebra. We say a function g is the inverse function of function f if, when you do the composition f of g of x, you get x, and when you do the composition g of f of x, you get x. Both compositions have to produce x. And then function g, can be denoted by the inverse function notation, f inverse. So let's do a quick example here. We're going to do the following for the functions. F of x equals 3 minus 4x, and g of x equals 3 minus x all over 4. Part A, we're going to show that f and g are inverses of each other. In part B, we're going to graph f and g and see that the graphs are symmetric about the line y equals x. That's a hallmark of the graph of a function and its inverse function. Graphically speaking, when you look at the graph of a function and its inverse function, they will be symmetric about the line y equals x. And then part C is kind of setting up something really important. We're going to verify that the point 1, -1 is on the graph of f, and that the point -1, 1 is on the graph of g. And we'll also verify that the point 2, -5 is on the graph of f, and the point -5, 2 is on the graph of g. So get this all written down, because at this time, I'm going to head off to the chalkboard to at least do parts A and C. I'll probably come back to the slides to do part B, because I can call up my graphing calculator for that. But let's head to the chalkboard and work through this example. Hey folks, in this example, gave you the functions f of x equals 3 minus 4x, and g of x equals 3 minus x over 4. Part A, I asked you to show that f and g are inverses of each other. Part B, graph f and g to see the graphs are symmetric about the line y equals x. I'm going to do that back on the slide so I can call up my graphing calculator. Then part C was verify that the point 1, -1 is on the graph of f, and the point -1, 1 is on the graph of g, as well as the point 2, -5 is on the graph of f, and the point -5, 2 is on the graph of g. So let's do part A. Show f and g are inverses of each other. So in order for them to be inverses of each other, we have to start off by doing the composition f of g of x. So f of g of x, that's f of 3 minus x over 4. So now we put 3 minus x over 4 into function f for x. And when we clean it up, the 4's would cancel out, so we have 3 minus, it'd be 3 minus 3, and then plus x, which simplifies down to x. So the composition f of g of x equals x. We also have to show that g of f of x equals x. Both compositions have to equal x. So let's do g composed with f of x. That's g of f of x. So that's g of, okay, f of x is 3 minus 4x. So now we evaluate function g at 3 minus 4x. So you know we take 3 minus 4x, put it in for x. So we get 3 minus 4x all over 4. Clean it up. 3 minus 3 is 0. Minus a negative 4x is positive 4x. And that simplifies down to x. So we have shown that f of g of x and g of f of x both equal x. That's how we know algebraically functions f and g are inverses of each other. So part C. Okay, we're supposed to show that the point 1, negative 1 is on the graph of f. Well, you know, here's f of x, 3 minus 4x. So f of 1 is 3 minus 4 times 1. That is negative 1. That tells us that the point 1, negative 1 is on the graph of f. Now let's show that negative 1, 1 is on the graph of g. So we find the g of negative 1 gives us 3 minus negative 1 over 4. 3 minus negative 1, that's positive 4. 4 over 4 is 1. So we've shown that the point negative 1, 1 is on the graph of g. And notice how the coordinates are just swapped. It's building up something we'll look at when we get back to the slides. To show 2, negative 5 is on the graph of f. Well, the f of 2 is 3 minus 4 times 2. 3 minus 8, that's negative 5. Yep, it's on the graph of f. To show negative 5 2's on the graph of g, well, let's find g of negative 5. So that's 3 minus negative 5 over 4. 3 minus negative 5 is 8. 8 divided by 4 is 2. So, yep, the point negative 5, 2 is on the graph of g. So let's head back to the slides where we're going to look at part B. We're going to show that the graphs, we're going to visually see that the graphs of f and g are symmetric about the line y equals x. That's a hallmark of the graph of a function and its inverse function. The graph of a function and its inverse function are symmetric about the line y equals x. And then we'll see how part C here was laying the foundation for a theorem. So let's head back to the slides and continue on with our review of inverse functions.
All right, folks, I said I would do part B of the example here back at the slides because I can use my calculator very quickly. I've already put into y1 function f, 3 minus 4x, and in y sub 2 I've put function g, 3 minus x over 4. So let's go ahead and look at the graph. All right, so, you know, there are the graphs. The blue one is 3 minus 4x. The red graph is function g, 3 minus x over 4. And we're supposed to see that these graphs are symmetric about the line y equals x. So let me come back to my y equals menu, and let me sketch in the line y equals x. So there comes the line y equals x.
And yeah, to me, it looks like we do have symmetry about the line y equals x. So the graph of a function and its inverse function will be symmetric about the line y equals x. That's something old. Hopefully you remember that from college algebra. Now I said part C was setting something up. So we verified that that was true. Part C was true. And part C, it serves as motivation for the following theorem. If the graph of f contains the point AB, that's true if and only if the graph of f inverse contains the point BA. Folks, this theorem it seems very simple, very basic. It's really important. It's actually a theorem we are going to prove. That's the importance of this theorem. And I think it's a proof we can make sense of and we can do pretty quickly here. So here's the proof. First off, if the point AB is on the graph of f, that means when we evaluate the function at A, we get B. So AB on the graph of f means f of A is equal to B. Nothing new or earth-shattering there. This means we can write f inverse of B. Okay, we can replace that B with f of A. So we can write f inverse of B as f inverse of f of A. Nothing earth-shattering there, just a simple substitution. F of A is B, so we substitute f of A in for B. So here's where we're at. We have f inverse of B equals f inverse of f of A. But remember, a function and its inverse function undo each other. So when we do f inverse of f of A, well, that has to simplify down to A. They undo each other. So if we have f inverse of B equals A, that means the point BA is on the graph of f inverse. And that's all there is to this proof. So continuing on, a natural question that we have, you should have had back in college algebra, and it's a good question to have, is do all functions out there in function land have an inverse function? And the answer to that question is no. So then a natural follow-up question should be, well, what type of functions have inverse functions? And the answer to that is in the following theorem. A function has an inverse function if and only if it is a special function called a one-to-one function. Now, some of you, I have in parentheses here in HLT, some of you may remember that you can graphically determine if a function is a one-to-one function by employing the horizontal line test. That's what HLT stands for, horizontal line test. And the horizontal line test said, look at the graph of a function. If you can draw a horizontal line, it only takes one. If you can draw a horizontal line that intersects the graph in more than one point, then it is not a one-to-one function. And if it's not one-to-one, it doesn't have an inverse function. So you would have seen this back in college algebra. Part 2 of the theorem is a little bit more of a calculus way. If your function is strictly monotonic on its domain, now remember that just means it's increasing on its domain or it's decreasing on its domain. Then the function is a one-to-one function and it has an inverse function. So let's do the following example. Which of the following has an inverse function? So get both of these written down in your notes because I'm going to head off to the chalkboard to do it, and I'm very particular about how we answer these questions. So pay attention to my particularness of answering the question, does it have an inverse function or does it not have an inverse function? So let's head off to the chalkboard and do parts A and B.
All right, folks, for this example, we're going to determine whether or not the function given has an inverse function. Okay, so now don't get me wrong. The first thing I would do when I'm asked if this has an inverse function, I would look at the graph and see what the graph is indicating. So I would encourage you to graph this function. And when you graph the function, you should say, you know what? It looks like it passes the horizontal line test. It looks like I can't draw a horizontal line that would intersect the graph in more than one point. So it looks like it passes the horizontal line test, which means it's a one-to-one function, which means it has an inverse function. And that would have been sufficient in college algebra, but not in calculus. So if you look at the graph and you think the graph is saying it has an inverse function because it's one-to-one, it passes the horizontal line test, you need to go a little bit further to convince me. And this is where the calculus comes into play the game. Because you can compute the derivative of this function. It's 3x squared plus 2. Now look at the derivative. No matter what you put in for x, no matter what number you put in for x, this derivative will always be positive. So for all x, the derivative is positive. If the derivative is positive for all values of x, that tells us the function is increasing everywhere. If the function is increasing everywhere, that tells us the function is a one-to-one function, which tells us that it does have an inverse function. Folks, I can create a function. I can create a third-degree polynomial function that has a relative max and a relative min, or a local max and a local min, so close together that when you graph it, you're going to believe it's one-to-one, but it's not one-to-one. That's why I'm saying graph it first. If you believe it passes the horizontal line test, which makes it a one-to-one function, which means it would have an inverse function, do a little bit of calculus to convince yourself, or to convince me, to convince anyone. On the other hand, this function, the first thing I do, I would look at the graph. And if you graph this one, it looks something like this. To me, it clearly fails the horizontal line test. There is a horizontal line that intersects the graph in 3 points. Since it clearly fails the horizontal line test, that means it is not one-to-one. There is no inverse function. You don't have to do any more. When your graph clearly shows it fails the horizontal line test, you're good. It's only when the graph is showing, yeah, it looks like it's one-to-one, that you have to do a little bit more work. So, all right, folks, let's head back to the slides and see what more, or what the next topic is on reviewing inverse functions.
All right, so you saw how I'm a little particular in that last example, that in part A, I said if you looked at the graph seemed to indicate that it would pass the horizontal line test. And in college algebra, it was fine to say it has an inverse function because it passes the horizontal line test, but it's not okay in calculus. The graph tells us we believe it's one-to-one and it has an inverse function. When we have that belief, we then need to employ calculus to verify that belief, which, as we saw in part A, we had to get the derivative, and we saw the derivative was positive everywhere, which meant the function was increasing everywhere, which meant that it was one-to-one and it had an inverse function. On the other hand, in part B, I said look at the graph. If you could look at the graph and clearly see that it fails the horizontal line test, that there was one horizontal line you could draw that intersected the graph in more than one point, then you were done. You could just say it clearly fails the horizontal line test. It is not one-to-one. Therefore, it does not have an inverse function. So that was my peculiarity, or my, how you have to be kind of specific depending upon what the graph indicates. So folks, now that we know, or now that we've reviewed when, or I should say what type a function has an inverse function, how do we determine the inverse function? Well, in this next example, I'll review the process to do this, and you would have seen this process in a college algebra course. So here we're going to determine f inverse for the function f of x equals 2x plus 3. So, I'm going to head off to the chalkboard and work through this.
All right, the next topic of review is, now that we know when a function is one-to-one and it does have an inverse function, it's the process we go through to determine the inverse function. So here's a function, f of x equals 2x plus 3. I know it's a one-to-one function because it's a linear function, so I know an inverse function exists. So let's find the inverse function. And you would have seen something like this in college algebra. Remember step 1, I'll label these. Step 1, replace f of x with y. Step 2 was to switch the x's and y's. Step 3 was to take this and solve it for y. So you would subtract 3 from both sides, divide both sides by 2. Step 4, replace y with the appropriate inverse function notation. So since the function was called f of x, the appropriate inverse function notation is f inverse of x. And then step 5, some people say step 5 is to do the compositions to verify that they are inverses. I'm going to trust that we did everything correct. And I say step 5 is to make sure you have that domain range agreement that must exist between a function and its inverse function. In other words, remember, the domain of the function must equal exactly the range of the inverse function. The range of the function must equal exactly the domain of the inverse function. It's pretty quick for this one because a linear function, 2x plus 3, has a domain of all real numbers and a range of all real numbers. This too is a linear function which has a domain of all reals and a range of all reals. So we do have that domain range agreement. So that was a quick review of how you would find an inverse function. Let's head back to the slides and see what the next review topic is.
All right, hopefully you remembered that process in determining once you have a one-to-one function, that has an inverse function, the process you go through to determine what the inverse function is. At this time, I need to head back to the chalkboard because we need to review a special topic called restricting the domain for certain functions. You would have been introduced to the concept of restricting the domain in college algebra. It became really important in trigonometry when we started to talk about the inverse trig functions. So let's head back to the chalkboard and see what I have to say about restricting the domain.
All right, I said we were going to come to the chalkboard to discuss this process called restricting the domain. And as an example of what this is all about, let's consider an old familiar function, f of x equals x squared. This is the graph. That's the domain of x squared. That's the range. As it is right now, f of x equals x squared does not have an inverse function. It does not pass the horizontal line test. But you know, and I know, there is a function out there that is the inverse function of x squared. Remember, an inverse function will undo whatever the function has done. And we know there is a function out there that undoes
the squaring, and it's called the square root function. We know square root x is the inverse of x squared, but x squared clearly doesn't have an inverse function. This is where restricting the domain comes in. You can look at a function like this that's not one-to-one, and if you can restrict the domain, but you have to keep the original range intact. So if you can restrict the domain while keeping the original range intact, and on that restricted domain you have something that is one-to-one, you can then talk about an inverse function. I can think of two ways to restrict the domain for x squared that preserves the range. Way one, just consider the function on the interval 0 to infinity. So it's kind of like ignore this part of the graph, the left part of the graph. Clearly that is one-to-one, and it does preserve the range. The second way we could restrict the domain is, well, just consider the domain to go from negative infinity to 0. So it's like ignore the right part of the graph. We would still preserve the range going from 0 to infinity. Now, between those two ways of restricting the domain, mathematicians many years ago, well before when I was born, decided to restrict the domain on x squared to 0 to infinity, so it would just be this piece of the graph of x squared, which is one-to-one, and it does have an inverse function. And we know the inverse function. I'm going to put the inverse function up here. We know the inverse function is square root x. And we know the domain of square root x is 0 to infinity. And the range of square root x is 0 to infinity. Notice how the domain of the function matches exactly the range of the inverse. And the range of the function matches exactly the domain of the inverse. And we know what the graph of square root x looks like. It does something like this, which is definitely, those graphs are definitely symmetric about the line y equals x. So I felt we needed to talk about restricting the domain because, coming up soon in this chapter, we're going to look at the inverse trig functions, which most definitely, deal with restricted domains. But let's head back to the slides and see what the next topic is.
All right, so at the chalkboard, I used the function x squared to get across the concept of restricting the domain. Thing to always remember, when you restrict the domain, you have to preserve the original range of the function. All right, let's see what's next. Well, the next item is this. It's going to be a really powerful theorem, folks. F is a function that's differentiable on an open interval I. If f has an inverse function that I'll call g, then the inverse function g is differentiable at any value of x for which f prime of g of x does not equal 0. In fact, g prime of x, so the derivative of the inverse function, is equal to 1 over f prime of g of x, as long as f prime of g of x does not equal 0. Folks, this theorem is really powerful. We are going to need this theorem. We are going to use this theorem coming up soon, and in a section that's coming up soon, to determine the derivative of a function that it's kind of a shocking result. And we're going to need this theorem in order to do that. So for that reason, I'm going to run you through the proof of this theorem. It's a very short proof.
So first off, the theorem is saying f and g are inverses of each other. Well, if f and g are inverses, we know the composition f of g of x must equal x. Well, why don't we differentiate with respect to x both sides of that equation? So here we are ddxing both sides of the equation f of g of x equals x. Now, folks, notice on the left side, when we ddx f of g of x, a composition of functions, that's going to require us just to write down what the chain rule said. On the right side, well, we know the derivative with respect to x of x, we know that derivative is 1. So on the left, the chain rule tells us f prime of g of x times g prime of x. The right side of the equation, we have 1. So to get g prime of x from the equation we're at right now, we're just going to divide both sides of the equation by f prime of g of x. And we have proven the theorem. All right, now hopefully you do have the theorem written down because I have to go to the next slide and tell you really what the moral of that theorem is. It's hard to see in the words what the moral of the theorem is. But so the moral of that previous theorem, the one we just proved, combined with an earlier theorem in this section that we proved. I mean, what we saw earlier in this section is if AB is on the graph of F, then BA is on the graph of F inverse. That's the old theorem we saw earlier in this section that we proved. What this theorem we just looked at and the theorem we just proved, the g prime of x equals 1 over f prime of g of x. The slope, it's telling us the moral is telling us that the slope at point AB on the graph of f and the slope at point BA that's on the graph of the inverse function, they are reciprocals. Now, I know you look at that theorem that we just proved, and it's hard to see that really that's what the moral of the theorem is. But that's why I'm here, to let you in on that. So let's do a quick example. We're going to look at the function x cubed plus 2x minus 1. We are going to find the slope of the inverse function at the point 2, 1. And we do not need to get the inverse function in order to answer this question. We're going to use the power of what's at the top of this slide. So please write this down because, I'm heading off to the chalkboard to work through it. All right, folks, this example, I think this is some pretty cool, neat stuff. I said, consider this function, and I asked you to find the slope of f inverse at the point 2, 1. What's cool about this is, for this function, you go through that 5-step process to try to find the inverse function, you wouldn't be able to. You just wouldn't be able to do it. You can't do it algebraically. So we're going to find the slope of f inverse. We don't even know what f inverse is, but we're going to find the slope of f inverse at the point 2, 1. Notice this is the same thing as, I could have written it down as f inverse prime of 2. The book may do something like that in a homework problem, I'm not sure, but it's the same thing. So here's the first thing that I notice. I even write this down. It's the first thing I notice. We are told that the point 2, 1 is on the graph of the inverse function. Well, if 2, 1 is on the graph of the inverse function, that implies the point 1, 2 is on the graph of the function. The slope at 1, 2 and the slope at 2, 1 are reciprocals of each other. That's what I just said back on the slides. So we can get the slope at the point 1, 2 on the graph of the function. We have the function. We can compute the derivative of the function. Remember, derivative gives us slope. So we have the derivative. We can evaluate the derivative at 1 to tell us the slope. So we know the slope on function f at the point 1, 2 is 5. That tells us the slope of the inverse function at 2, 1 is the reciprocal of 5, which is 1/5. And that's all there is to this one. So at this time, we're done in section 7.1. Wasn't a whole lot of calculus in this section. It was a lot of algebra review. But there was a little bit of calculus, and you notice we did prove a couple of theorems because something really big is brewing in the next section. That's why we proved those theorems. But at this time, you can do the exercises in section 7.1. So go do the section 7.1 exercises, and thanks for watching.